Okay, I think we're going to get started now. So welcome everyone. My name is Ida Fernandez. I'm the Executive Director for the Imagine SPORE Network. Thank you for joining us today and welcome to our session from our network's monthly training webinar series. And these webinars are really aimed at building capacity and improving the design of future research studies. We're really excited about today's talk on statistics and research led by biostatistician Gabrielle Boucher. I'm just going to go over a few housekeeping items before we get started though. So first of all, just please ensure to keep yourself on mute throughout the presentation so we can minimize any background noise. We're allotting 10 to 15 minutes at the end of the webinar for Q&A. So we encourage you to type in your questions using the chat box feature at the bottom of your screen. And you can enter that question anytime throughout the presentation, and then I'll read them at the end of our presentation for our presenter to answer. Following the meeting, you'll also receive a link to complete an evaluation survey. So please give us your feedback so we can continue to improve these sessions moving forward. Also, once you've completed the survey, it allows us to track your participation for these webinars, especially for those seeking CanMed credits. Finally, we do record these sessions. We archive them on our website for future viewing. So please visit imaginespore.com if you'd like to share it with your colleagues who weren't able to join us today, or just check out some of our previous training sessions as well. Great. So just next slide. Excellent. So just a little bit about the Imagine Network. I hope most of you know who we are. We're a research network investigating the interactions between inflammation, microbiome, diet, and mental health in patients with inflammatory bowel disease and irritable bowel syndrome. Our mission is to transform the management of IBD and IBS and associated mental health issues with these disorders. Before we get started, obviously, I'd like to introduce you all to our presenter today, Gabrielle Boucher. So Gabrielle is affiliated with the Montreal Heart Institute. She's worked very closely with biologists for over 10 years and is familiar with common challenges in experimental biology. She's provided support in a variety of different areas, including genetics, molecular biology, immunology, proteomics, and metabolomics. Her expertise extends from experimental design to quality control, statistical analysis, and data interpretation. So I'm now very happy to pass it over to Gabrielle for today's talk. Thank you.
Okay, so these are just the first few slides about disclosures. I have no disclosures. The CanMed's role, learning objectives. As Ida said, I'm a statistician, a biostatistician. I did a master's degree in mathematics, statistics, and I have been working for 12 years now in genetics and biology lab. So I learned a lot from the people I work with about the problems they get into when trying to use statistics to help with their experiment. So today, the objectives are to recognize errors at the design stage, identify how to effectively interpret data, and share study results, understand how to get the most out of your study and experiment. I won't be presenting much mathematics stuff. It's mostly some idea for you to take home, a few take-home messages. So the first slide I decided to put here is that a statistician is not a superhero. And this is something I've learned from many people I work with. I have many statistician friends, and we all have this feeling that sometimes we are being called by scientists to save an experiment, to say, oh, please help me, Lord. So, but a statistician can help you with the design, but it can help you work with you to design your experiment, not just doing do it alone. We need your help, but we can help you with the design or to identify and sometimes correct some issues. We can perform the optimal analysis of the data, create graphical displays, interpret the result, etc. But we can't save an experiment. So this is why the most important step for optimal statistical analysis is at the design stage, because after the fact, after the experiment is finished, I can help you with the analysis if you don't know how to do a regression, but I can't redo the design. So for most scientists, the most important statistical skill to build is designing a study. So this is why the first part is really about design, which is the foundation of your experiment. And it's up to you to decide what kind of foundation you want, a solid one or one that will crumble at the first issue. So the first thing I want to talk to you is inference. So statistics, we often think about a lot of numbers and formula, but it is much more about inference, which are linked to logical roots. Of course, mathematicians also created formula to illustrate logical roots. I won't explain you how it works, but we do that. We study logical roots. It's much more about what can we say from the information we have. And we use mathematics as a tool to do that. And at the stage of the design, it's about what information do we need to answer a question, your question as a scientist. So statistical inference is we start with information from samples and some assumptions to build a conclusion about a population. These assumptions can be about the probability distribution of the observations or some a priori information you have. For example, if you ever work with a Bayesian statistician, or representativity of the samples, or any other kind of assumptions you have. And then we use math tools to do that. These are tools, it's not the goal. And for some people, it looks like it's the goal, but it's not. It really is just a tool. And it's important also to think about which population am I talking about. It's really important. So who are you talking about? Suppose I have a question. Are men taller than women? So I build my experiment, I sampled men and women, and in my sample, women are taller than men. But I took the samples in my cousins. So the inference will be restricted to my family. I can make an assumption saying, well, my family is representative of my country. Then I would say women are taller than men in my country. But of course, it's not true. So what about the conclusion? It's not valid. It's not necessarily false, but it's not a valid conclusion. So you would say, we don't do that in science. Well, we do it a lot. So here is just a small example with cells. Suppose you start with cells and your question is survival better in treated cells? And you have some untreated versus treated cells. So you have your sample, and in your sample, survival is better in treated cells. But all those cells come from the same cell line. Then the inference will be restricted to this cell line. You can make an assumption saying this cell line is representative of all cells. And this assumption is behind a lot of papers that are actually published. And then you will say the treatment increased cell survival overall. But if this assumption is not true, what about the conclusion? So only one false assumption completely invalidates the conclusion. And it's important to understand that, because it's not that it's false at the end, it's just that it's not valid anymore. Let's return to our question about men being taller than women. Now, let's suppose that I took 3 men and 3 women. Then individual here will be my experimental unit, my biological sample, and I have an N of 3 for each group. Suppose I measure them 10 times. I will have technical replicates. I will then have a very precise estimate for these 6 people. And I can then conclude with certainty about these 6 people, about the difference between those 3 men and these 3 women. And I will have, if I do a statistical test, a t-test, for example, I will have a very, very significant p-value using all those measures for the particular question about those 3 men versus those 3 females. But I still have N of 3 per group to compare men and women overall as a population level. If I redo the whole experiment with the same people, I will still have N of 3 to compare the 2 groups, to compare men and women. And you say, no, we don't do that. But actually, there are many, many papers where people actually do that. They take a few samples, take a lot of measures, and they don't know how to handle the data properly. And then they would say, well, I have N of 60. No, you have N of 3 per group. So this is where we're talking about the kind of replicates you have. You can have biological replicates, which are at the level of the biological sample or the individual, experimental at the level of treatment, technical at the level of the measure itself. But it's not always that simple to define it and that clear cut. It's just a broad definition that people use. And even from a statistical point of view, we don't even do that. We talk about the experimental unit and the population. And to some level, at saying at which level of inference we are. So let's look at one kind of experiment we can see. Suppose I have Phil and I draw blood on some day, and then I isolated cells. Honestly, I don't do that. Some people in the lab would. So we isolated cells in tubes. And then I take one of those tubes, I plate the cells, we treat some of the cells and some we left them untreated. And then we repeat the measures. What do we have here? Well, the experimental unit is the well. It's not each of the cells. It's a well as a whole, because it's the whole well you are treating or not. So the experimental unit is the well. The inference will be on the tube, because all the cells come from this exact tube. They come from the same tube. And I then have an N of 3 to talk about this particular tube of cells. And the repeated measure will give us an increased precision on the measure. It's not increasing the sample sample size, sorry. It's increasing the precision of the measure, which can be really, really useful if you have noise in your measure. And then if I make the assumption that the tube is representative of Phil as an individual, then I can say, well, my inference will be on Phil. But I still have N of 1 for the inference in the population as a whole. So there are limitations on the inference you can do. So what you can say from your experiment. Statistical analysis are performed at on the experimental units, which will define the level of inference you can have. If you want a higher level of inference, so if you want to talk about a larger population, you will have to increase the sample size at the higher level or make more assumptions. But this is dangerous. Sometimes we can make those assumptions because there are some previous experiments you can work with to build those assumptions. But if you don't, it's dangerous because it can invalidate your conclusion. So now for the same kind of experiment, suppose now we took 3 people And then we plated cells for each of those people. And for each one, we took a pair of wells. One is treated, one is untreated. And then we can repeat the measures and or the treatment. The experimental unit is still the well, but it's a pair of well per individual. Then the inference is on the population as a whole, with N of 3 for this particular question about the population. And my repeated measure will reduce the experimental noise. So as a general rule, because this is something I'm often asked for, how do I deal with the different kind of the replicates I have? So at the design stage, you will have to maximize the sample size at the higher level possible. So you will maximize the number of biological samples. If you have heterogeneous or noisy steps, you will need to increase repeats because else you will have a lot of noise. But if you have limited resource and you need to make a choice, you can't do everything. You should prioritize biological samples over repeats. This is a general rule because if the experimental process is really noisy, more noisy than individual variation, you should consult a statistician because there will be a trade-off between the two. And here is about recruiting human samples, because I know some people here in this consortium do that, actually recruiting samples. A particular word of caution is about cases versus controls, which is a very popular design. So we will usually select the cases based on some conditions, some tests they did, some symptoms they have. So we select them. Then we will take the controls usually as not diseased. We can take them without this question of being or not being diseased, but most of the time people will ask them for being not diseased. So we will also have a few conditions about that. But it's really important to think at the end, in this whole process, are they from the same population? Because the controls should be at risk, but not affected. And this is not such a simple question here to select the controls that way, because will you take them from the general population? Will you take them, suppose you're looking at or heart disease? Will you take diabetics? Will you take people with cholesterol? What will be your baseline? Many times people would take convenience controls from biobank. This is, as we said, convenient. But we should always think about how and why were they recruited. Sometimes they are more healthy than the general population, or more healthy at least than the controls you should use for your study. For example, in one study, we used biobank control for a genetic study, which wasn't such an issue. In genetics, there are some things we need to care more or less about, but we took them. And the controls, we then wanted to look at other features than just genetics, and we were looking at smoking. And what we saw is that our controls, the difference in smoking rate was very, very high between our cases and our controls. We were wondering, because it was known that smoking was a risk factor, but not to that extent. And then I looked a bit more and realized that my controls were smoking much less than the overall population, because they were a more healthy population. They were nurses, they were doctors, because they were taken from an hospital, from the staff. So they were not representative of the population. In some other situation, you can have people in the biobank who are more sick, actually, because they are patients from the hospital that came to the hospital for something else. So you might end up, if you don't take enough care here to compare disease 1, the one you are studying, with disease 2, the one that you don't want to study, but that represent people that came to the hospital. And this often happens when you look at a specific lab test, for example, that is only performed from people who are sick. So you need to think about why those people needed to take this exam. And sometimes it's a good thing to have two different sets of control at the end, some that are more populational and some others who are selected based on those kind of tests. Some setting will say, ask case to refer a friend, for example. This is a good way of selecting control, usually, not the only one, not always perfect, but it is usually a good way. I've seen some study where the cases were taken in the clinic and they were much older because this is a disease in old people, and the controls were populational and they were young. And this was a very big problem because this is metabolomics, and metabolomics is affected by age. You need to think about those kind of issues. So the selection of controls is as important as the selection of cases, and maybe even more. And this is something people do not realize. So I would suggest anyone doing those kind of study to read books about epidemiology and how to select cases and controls. Another thing that can happen in a study is survivorship bias. And this is a very, I would say, cool story. I won't go into much detail. You can find it on the internet. But the idea is, and during World War II, the Allies wanted to protect the planes about being shot. So they looked at the planes they had and looked at where were the bullet holes on the plane. And they found out that it was on the wings and tails. So they were thinking, okay, so we will add some plating over those. And then they asked statisticians. And these statisticians told them, well, these are surviving planes. So these are the planes you have. Where are the missing bullet holes? Well, those missing bullet holes are your missing data, and they are on the lost planes. So they are on the planes you can see because they were shut down, and so you don't have them. So where should you protect the plane? It's around the engine and around the cockpit, but you don't see it in your data. So your missing data here was more informative than what you actually see. So you should always put a lot of caution about non-random missingness and your blind spots. So this survivorship bias, I've seen it at some early stage of the COVID pandemic, and there was at some point I saw this in the media, and some study told us that smoking was actually protective for COVID. So it looked weird. So I looked a bit more into the study itself. It was a preprint, not even a preprint. It was not already reviewed. So they took patients admitted in the hospitals. So they had smokers and non-smokers. And then they compared to the general population. So we could already ask whether it's a good comparison, it's a good control population, but well, suppose it is. And they saw that there were less smokers in hospitalized patients than in general population. So they said smoking was a protection factor for getting COVID. So I've seen many people saying actually on Facebook, etc., that, oh, don't stop smoking. Smoking is protecting you against COVID. I mean, this is a real thing. But at the end of the paper, they were saying, well, there are some limitation in our study. We excluded intensive care and death. So, and it was known from other study that in intensive care and death, there were much more smokers in those severe cases. So here, their conclusion is completely false. It's completely wrong. The way they did their study, due to survivorship bias, they did a wrong conclusions. And it's not a limitation here. It's a major flaw. So you should protect your studies against those kind of major flaws. Talking about flaw, we all learned about Murphy's Law. And we think about these toes falling on the wrong side, and we think about the fatality. But Murphy's Law was built for experiment. From an experiment, it was an invitation to consider everything that could possibly go wrong and protect yourself against it. So I also invite you to learn about the story behind. But here in science, we can think about batch effect, position effect, time trend, loss of samples, because what will happen if some of them fails, or equipment failure, or anything that could go wrong. And then you want to protect your experiment and your all hard work. And this, it must be done at the design stage. So I would suggest that you always consider that there will be batch, plate, or time effect. Even if someone tell you that, oh no, there won't be any, I would put a standard curve, I will have reference samples. No, always assume there will be batch effect. And then you can do complete randomization of your samples. But often it's not feasible. So once I was younger, I was in the lab, and some student came to me and said, I have many samples to put on different plates, and how can I protect myself against position effect? And I said, well, just randomize everything on the plates. And she looked at me and said, okay, that would drive me crazy. We must do something else. So that's not usually feasible. And it's not as reliable as it should, because on average, you will have a balanced design, but not always. So you should balance the samples between the plates, days, batches, etc., and break patterns as much as possible without losing your mind. So suppose a very small study here, you have some cases, you have some controls, you want to let's suppose here is a plate, but it would be the same if you want to genotype them on batches, and you can then do them all together. You can do a design where you do all your cases on one side, all your controls on the other side, but this is really hoping for problem here. The one thing that you can do is here on the plate, you would do half and half, but here there could be a position effect. So you could say, well, let's just break the pattern. Let's just put them just in a way that if for some reason the right side of the plate we get higher signal, I will completely mess up my experiment. So it's not randomized, it's just breaking the pattern. You can do also randomization. For example, if you want to do a test for a treatment, and then you want to randomize, suppose you have the people here, so men and females, and then you want to test whether the treatment work, and you just randomize into 2 groups. This is a standard way of doing clinical stuff. But here, well, Murphy's Law, you end up having more men in one group and more women in the other group. So what will happen if gender is a confounder to the outcome? I've seen this actually also in COVID for some treatment, and they end up with this kind of issue. So if you know that you have some factor that could be a confounder, I would suggest that you just split the group in 2 and then randomize the men in 2 groups, randomize the women in 2 groups, and then you will apply the treatment. The rest, the other factor will be taken care of by the randomization, but the ones you know could be a problem, you should balance, really force the design to be balanced. So what you can do to cover your back for this kind of issue: keep the samples you want to compare close together to avoid artifact. And when I say the samples you want to compare, it will be case versus control, treated versus untreated, etc. Close together would be in space, on plates, in time, or in batch of reactive, in the staff doing the manipulation in the lab. Then keep minimal distance between biological samples. This is to reduce between sample noise and increase power. Then technical replicates can be confounded with batches. It's not an issue. When you have limited resource, you need to balance and or randomize and balance of important condition. And remember to break pattern or as much as possible. Here, there's also the point of power. Statistical power, I won't go into much detail, but it's more about the probability of detecting a given effect size, or about the precision you can get about an estimate. It depends on the sample size. A small sample size will have small power, so you have a probability of you can have a probability of detecting the effect that will be close to your risk of false positive, which means that you don't have enough information to say anything, which will lead to a lack of replication, wasted work and resources, and also depressed scientists. What you should do is estimate sample size so that it will be enough to detect the smallest relevant effect size that you want to be able to detect. Then more sample would be best. But when you increase sample size, remember that yes, you will increase your power to detect your true effect, which is good. And you also increase the power to detect any kind of artifact from bias you can have in your study. And this is the point that many people don't understand. If when you increase sample size, you need also to decrease the risk of artifact. It's really important because you will get very small artifact. And I've seen this in genetic study, for example, where people will say, wow, there's not so much batch issue when we genotype people. It's just very small batch effect. But then they increase the sample size, they increase it, and then these small effect would be significant. So it's even more important to reduce any possible bias with larger sample size. So this is a citation from Marvel here. So this was the part about the design. So now I'll just go very quickly about showing some results, but I can't do everything, but because everything is a special case, but just a few take-home messages. So often when we report results, we are reporting the mean. Mean can be useful, but it's not always the best tool. So most of you probably learn in class and seen the famous normal distribution. Where for this distribution, you have that on the x-axis here is the value you can get, and on the y-axis is more or less the probability of getting it, the frequency of getting it. And here you will have that the mean is equal to the median, which is also equal to the mode. The median is the value in the middle. The mode is the most likely value. It's the top, it's the peak of the distribution, is the most frequent one. Using the mean is good for central measure and symmetric distribution, like this famous normal distribution. It's also easy to do statistics with mean for some mathematical reason. But more often, we don't have a normal distribution when we perform analysis. So we can get a symmetric distribution like this, where the mean can be somehow misleading. And in particular, you will have the log normal distribution that will arise very often in biology, where the mean is is not the same as the median, and the median and the mode are exactly the same. And many distribution in biology follow log normal distribution. And I think it's a shame that biologists don't learn that when they do statistical classes. Then median is a better choice here. And we call it the log normal for some reason. So we have the when you have the accumulation of random additive effects, you will get the formal normal distribution for your values. This can be proven with math. If you have an accumulation of random multiplicative effect, you will get instead the log normal distribution. So when you talk about double or threefolds or fold changes, well, you can think that these are multiplicative effect and that the distribution will be log normal. And it's log normal because when we log transform it, it's back, the distribution will be back to the famous normal distribution, which is really convenient to do stats because you learn to do a t-test, for example. So it's not a problem here after you log transform your data. So that's why often in biology, we log transform the data. And that's something most of you never learn, but that's the reason why we do it. And then what it also means is that what was multiplicative on the original scale, which will now be additive on the log scale. So this is also very convenient for statistical analysis because we usually look for additive effect when we do stats, for example, a t-test. And this additive effect, you can then transform it back to a fold change. Once the stats are done, you have your p-value, etc. And just this is from the law of logarithms, and I just want to highlight the fact that your math teacher was right in high school that this will be useful at some point in your life. Then you will need to choose your error once you selected that you want to show the median or something else. So if you start with a normal distribution, which will look like this when you take samples out of it, if you take 10 of them, you average it, well, the average will be close to 0, which is the mean you expect here. But there will be some error. Here it will be a large error. If you take 100 samples instead, this error you make about for using the average as an estimator for the mean will be smaller. And this is then an error that is inversely proportional to n. And this is what we call the standard error of the mean. So standard deviation is a characteristic of the population, is how variable the data will be. Standard error is a characteristic of your estimation. It's how precise you are when you do the estimation. So when you report your results, if you want to show between measure variation, for example, or variation in the population, or you have replicates and you want to show it's consistent, you will use standard deviation. But you can also use quartile and interquartile range. If you want to show the precision on your estimate, or you want to show that your results are significant, you will need to show standard error. So often, this is a question that people often ask me, what kind of error should I put on my graph? It depends on what you want to show. And there's no just one answer. And someone saying it's always standard deviation, it's false, or it's always standard error, it will be false also. It depends on what you want to show. And if you want to show significance of results, you can also show the confidence interval, which is more informative, but depends on more assumptions. And more importantly, always state the error used. The confidence interval is related to the standard deviation and the sample size in two ways. So it starts with the standard error, and then you also still need the sample size to build the confidence interval itself. What I want to focus more about is the interpretation of this. Most people would think about it as being, oh, I have 95% chances that the mean is in the interval. This is statistically wrong, at least if you're a frequentist, but it's not a big issue. I mean, the real thing we should say is 95% chances that such an interval include the mean, but it's a subtlety. If you understand that you have 95% chances that the mean is in the interval, it's already great for your interpretation about what you're looking at. Many people will perform statistical testing, which is a special kind of inference, but it's not the only one. So we'll start with an hypothesis, usually that there's no difference. So this is the hypothesis you want to exclude with certainty. You want to be sure that if you say it's wrong, it's false, it will be false. Then you will have a type 1 error. Usually we write it as alpha and we use 5%. This is the accepted risk of false positive. This is chosen by the scientists, and it could be anything else that's that 5%. It doesn't have to be 5%. This is also what we call the significance threshold of the test. The type 2 error will be, which is 1 minus the power, is the resulting risk of false negative. And it depends on your sample size, your effect size, and the error you chose. So there's a trade-off here to make between the cost of the false positive versus the cost of the false negative. And you need to make the choice. So often people are saying, what should I use as a threshold? Well, what kind of risk do you accept? Do you accept more type 1 error to get more power, or vice versa? And sometimes it's worse to have a false negative than having a false positive. And this is something that people should keep in mind when they choose their threshold, because this 5% is not solid rock. I mean, people use it, but there's no true reason. Then are you asking the right question also doing that? Because people say, okay, let's test no difference or no effect. But is this really your question? Because sometimes it's a trivial question. Sometimes we know H0 is false. We apply a treatment that we know will have an effect. What we want to know is, what is the effect size? So then why use p-values from testing no effect? If what you are interested in is the effect size, then you should focus more on the estimation of the parameters and the errors. And confidence intervals here have a more general interpretation, because instead of just saying, well, it's not 0 here, we can say it's not 0, it's negative, it's also lower than 0.5. There's also with statistical tests, the issue that people will say, okay, let's test no difference in mean between treated and untreated. The p-value is not significant. They will say, well, there's no difference between the treated and untreated. But it's wrong because you can't say that. It's because maybe you just lack information to conclude. If you use a confidence interval, you can say that maybe the difference is smaller than a given value, or maybe there's a lack of information and that's why your p-value is not significant. If we look at those two confidence intervals, the top one here, we know that in both cases, the p-value would be larger than 5%, so we'd say it's not significant. But the top one, we know that the effect size is smaller than 0.5. The second one, we don't know, it's much larger, but so the second one will say, well, maybe I don't have enough information here. I should increase the sample size. So it's more general. It's more useful here to do confidence interval than just giving a p-value. So really fast, just about a few graphical display people use often, because I can't talk about everything. So pie chart is really popular as a display. There's this citation from a great statistician here that I kind of think is funny. I would say that humans are not good at comparing angles. So It's a pie chart should be used as a vulgarization tool when you show large difference to many people, and it's easy to just look at, like these difference here that I illustrate are large enough that we can capture it. But for direct comparison in scientific paper, you should use other kind of display. Like bar plot, like these one, which are really popular in biology. These are great, but we need to think about it correctly. Here, the height of the bar has a meaning. The zero has a meaning. So you wouldn't illustrate temperature, for example, as a bar plot, because the zero, what does zero mean? It doesn't mean that there's nothing. It's not even the same value if you use Celsius or Fahrenheit. So it's best used for the display of multiplicative effects. And then cutting the axis create a distortion of the effect size. So it usually should be avoided. And many people do that. But if you are to cut the axis, you probably are better to use another kind of display. And it's often a good idea to add the dots of the actual values if you have only a few ones. If you have a small sample size, it usually is a good idea to put the values themselves. Box plots is another kind of displays that people likes, and it's great. It's best to use to show the distribution of the samples. You will have the median, the quartiles, the outliers. It can be great, but it's not to show statistical significance. Here we don't know if the difference between those two groups are significant. It's just the distribution here, like showing the standard deviation. It's not about significance. So if you want to show everything, you could use those two kind of display, and you have the whole picture here. So some close to the conclusion is that statistics should serve science, not the other way around. What I've seen often is that people perform an experiment hoping that they will get a significant p-value to publish. But we should keep in mind that we should use the statistic to answer the question about the science. And sometimes an insignificant p-value is still really informative if you have a large sample size. So at the end of the day, if you need help about the design, about a complex experiment, something like complex models or repeated measure ANOVA, time series, these are kind of difficult to do by yourself. You can ask a statistician to help you, but don't think that we will just save the experiment at the end of the day. So thank you.
Thank you so much, Gabrielle. That's very informative, and really appreciate your insight, especially around how to best represent your data. That was very enlightening. So I'm just going to, again, give people a few minutes if they have, we do have a couple of minutes here to answer some questions. So please go ahead and enter them in the chat box. In the meantime, while we're waiting for people to enter questions, I do want to obviously thank all of our supporters for Imagine that allow us the opportunity to present these training webinars. So thank you to all our supporters. And just waiting to see it. Just in the meantime, then, Gabrielle, I know you obviously suggesting that trainees look to get some support from statisticians. And it seems like early on in their design phase, is that something that people can seek out and get that advice from at that stage, or are they normally just sort of engaged towards the end of their studies when they're presenting or analyzing their data?
That's what people should do, is really at the early stages of their experiment, at the design stage. And yeah, of course, what I often see is that people come to me at the end of the day, even people I'm working with in the lab. I mean, I go to lunch with them and then they do their experiment and then they come to me, well, I need to analyze the data and I don't know, well, why didn't you come and just asked me, and we would have avoided a few issues just thinking about the design.
Great. Thank you. So a couple of questions coming through. So great talk. What about central limit theorem rather than log transformation for larger numbers?
The central limit theorem is in fact what I've shown. It's just that I haven't called it like this. I mean, sorry, it would maybe be trying to find my slide. No, it's not this one. I don't know why. Where it is. Okay. This one here. So this is the central limit theorem that says that additive accumulation of random additive effect would give you a normal distribution. So this is what the theorem says, but it is additive. But the fact is, and this one below is simply a consequence of the other one on top, that if you accumulate random effects that are multiplicative, you will get the log normal. These are the same theorem, it's just not stated the same. So the first one is additive because statistics were done historically with additive effects. So this is the central theorem. So, and so whatever you do, your data will follow these patterns. Of course, then, if you take some samples here and you take the average and your sample size is large enough, you will return back to a distribution that will be normal because you make you make an addition of different values. So the starting distribution is not important. It's the fact that it is additive that gets you to the famous normal, and the fact that that it's multiplicative that will yield the log normal.
So as a follow-up to that, we've got the comment here that central theorem states that although the distribution is skewed, the means will follow a normal distribution. So you can use parametric statistics?
Yeah, exactly. It's yes, you can. And in fact, most of the time, parametric statistics, if you have a sample size that is large enough, won't be problematic even if you have a highly skewed distribution. That's completely true. The point is, it's better to just start back to something that is more symmetric, and it's much more about how you will think about the results, how you will interpret the results, and also you will still have much more outlier if you don't log transform beforehand. So when you know you have a log normal, or you think you have a log normal distribution, it's still better to log transform. And that's what we do usually in metabolomics and proteomics. We log transform. Why? Because we know the distribution will be log normal. And often if you have a small sample size, you're better off being closer to the normal than just hoping that on average you will get to the normal. Okay. So yes, it's true. I would still suggest to consider log transforming your data when you think about multiplicative effect. It's also a question of interpretation. If you look at, for example, qPCR data, and people sometimes say, okay, I have an effect on one experiment and I have another effect on the other. I don't know how to interpret because the units are completely arbitrary. But then you log transform and you will have the same effect size. It will be a twofold, it will be a threefold, and it would be the same in the two experiments, which you didn't have if you just look at the values. So.
Right. So another question here from another participant, and she says, so thank you for your talk. It's not related, the question specifically to your talk, but could you, when would you consider superiority versus non-inferiority study design?
I'm not sure I understand here, but I suppose we're talking about, because here I said a very a small kind of null hypothesis where you will say there's no effect, but you could say, okay, the effect is larger than that, then as a given value. You can do that. I don't know if that's what the person is talking about, but because you can do that, but if you do that, it's because you know it can't be smaller. So if you are testing again for one side of only one side, if you want to perform a one-sided test, it's because you know that it can't go the other way. So okay, so you can do it, but most of the time we do it on one, just one two-tail. But you can do it if you have good reason to. And sometimes it's even much better because you know it should go, what you want to test is in one direction.
Okay. From another participant, great talk. I'm actually not familiar with the meaning of geometric mean. How does it differ from the mean?
The geometric mean is, because this I haven't explained it in this particular setting here, but okay. So if you have your log normal transformation, you log transform, then you get the famous normal, you do the stat, you get an additive effect. Here, if you took log 2, you will have to do the opposite transformation to power the effect to get your multiplicative effect. So this is how we do it. So what is an arithmetic mean on your log transform data? So you just compute the mean. Basically, when you transform it back to the original scale, it will be a geometric mean. This is how we call it. You can also compute it by hand without doing the log transformation. Just instead of adding every values and dividing by 3 here, you will multiply all the value and then took the root. So that's what it means.
Great. Thank you, Gabrielle. So we have run out of time. I know we have one more question. Maybe, Gabrielle, if you wouldn't mind, I'll send you by email and we'll get back to the participant to answer that one. Really, again, appreciate your insight in a very complicated topic area for most people. And our feedback, obviously, from participants is that you did a wonderful job and used great examples to illustrate it. So thank you for your time. And thank you to all our participants that joined us today. Again, please complete the survey when you get the link in the coming days. And we look forward to your participation in future webinars. So thank you very much, everyone. Have a great day. Bye.